Hi everyone, my name is Dylan, and in this video I'll be presenting a paper from the 2024 MICCAI conference titled RDD-Net Randomized Joint Data Feature Augmentation and Deep Shallow Feature Fusion Networks for Automated Diagnosis of Glaucoma. This paper focuses on improving current AI models to automatically diagnose glaucoma, that is, whether a patient's fundus image has glaucoma or not. More specifically, it tries to solve the problem of domain generalization, where an AI model usually performs worse when evaluating on a fundus image that does not come from the domain that it is trained on. We'll proceed through the presentation as follows. We'll first go through the introduction, taking a look at the background problem and the previous works that tries to solve it. We'll then go through the proposed methodology of the paper, going through each component in detail. We'll then look at the paper's results and see if their methodology really does work or not. Finally, we'll end with a reproducibility demo, which is me cloning their GitHub repository and running their experiments on my own machine to see whether the results are as promised. So let's just go straight into it. Glaucoma is a neurodegenerative disorder marked by progressive damage to the optic nerve and the retinal nerve fiber layers, ultimately leading to visual field deficits like vision loss or blindness. Now, early detection is crucial as timely diagnosis of glaucoma, which leads to timely intervention, can prevent irreversible vision loss. Nowadays, AI has been rapidly advancing with deep learning techniques and computer-aided diagnosis systems, usually leveraging CNNs, convolutional neural networks, able to diagnose glaucoma with a high accuracy. The problem here is that it only performs well on images that comes from the same domain. Take, for example, an AI model trained only on the refuge dataset. It can evaluate well on images from refuge itself, but its performance drops significantly when tested on other datasets like Ramon or Origa. This happens because different datasets mean different medical devices or clinical conditions, resulting in images with different styles, such as varying colors, zoom levels, and resolutions, as you can see here. So, if the model is trained exclusively on refuge, it becomes good only at evaluating images similar to those in refuge. When it encounters images that look different, Ramon or Origa, for example, the performance worsens since the model isn't used to these unfamiliar styles. This paper aims to solve this exact problem by optimizing and improving the AI models. The goal is to enable them to evaluate effectively on various image domains beyond their original training dataset. This would create a more robust model suitable for real-world clinical settings, allowing deployment in multiple hospitals globally. There has been a number of existing solutions that tackles domain generalization through data level or feature level augmentation strategies. For instance, DIMIX dissects content and style, then synthesizes new images to enrich training data. TRI-D blends original and augmented feature statistics, introducing randomization in how features are distributed. CDD-SA focuses on contrastive domain disentanglement and style augmentation for segmentation tasks. GDR-Net simulates various image transformations and degradations to improve robustness. And MOX systematically mixes feature moments to encourage networks to learn from different distributions of mean and variance. While these studies are good at their time, these studies have common limitations, such that many rely on heuristics or empirical transformations, which don't fully capture the wide variety of changes seen in real clinical settings. This means that they mostly handle typical domain shifts, but aren't very effective when it comes to extreme or rare scenarios. And so this paper specifically aims to solve these shortcomings. By tackling domain generalization more effectively, the goal is to make AI models robust enough for real-world clinical settings, allowing reliable deployment across different hospitals and clinical environments. The paper proposes a framework called RDD-Net, which is built solely for robust domain generalization in glaucoma diagnosis. Treatment components in this framework are joint data feature augmentation with domain randomization, explicit-implicit augmentation randomization, and deep shallow feature fusion method. And so we'll take a detailed look into these three components in the following slides. Before we move on to the 3 modules proposed in the paper, I'd like to introduce the backbone model that forms the basis for this paper's methodology, which is RDD-Net. RDD-Net is specifically chosen for glaucoma classification because of its robust multi-path design and split attention mechanism, both of which are very well suited for handling variability in medical images from different devices and clinical settings. By design, RDD-Net is better at domain generalization tasks. So, just a little bit of historical context here. In 2015, Kai-Ming He and colleagues introduced RDD-Net. This was a true landmark in deep learning for one major reason. As neural networks grew in depth, they often faced the problem of vanishing gradients, causing training to fail. RDD-Net's game-changing idea was the identity skip connections, which you can see over here, which is essentially a direct link bypassing one or more layers. By having this shortcut, the backward flow of gradients is preserved, preventing them from becoming too small. This clever approach allowed researchers to build neural networks with over 50, 101, or even 152 layers. The RDD-Net here that is used in this paper uses 50 layers. The impact was immediate. RDD-Net and its variants rapidly became the go-to backbone for many computer vision tasks, from image classification, like glaucoma classification, to object detection and segmentation. Over time, more specialized versions emerged, RDD-Net's SE-Net, SK-Net, and ultimately RDD-Net, which is the focus here. Understanding the fundamental role of RDD-Net helps us see how RDD-Net builds on and extends these core principles. Now, RDD-Net didn't materialize in isolation. It's a product of key innovations from multiple earlier architectures. Let's highlight a few that played a big part. VGG-Net popularized a modular design, repeatedly stacking 3x3 convolutional blocks. And the advantage of this is that a standard block is easy to replicate, which simplifies both model creation and subsequent transfer learning. In fact, RDD-Net's idea of a repetitive bottleneck block is partly inspired by VGG's straightforward structure. Inception, a model created by Google, introduced multi-path processing. The network splits an input tensor into parallel branches with different kernel sizes, then concatenates the results. This concept of exploring multiple receptive fields simultaneously turned out to be incredibly powerful for extracting a wide range of features. RDD-Net took the multipath idea further by using grouped convolutions, also called the cardinality dimensions, over here. Instead of just making networks deeper or wider, RDD-Net emphasized having multiple parallel groups in the same layer, and this turned out to be a more efficient way to expand model capacity while keeping computational costs manageable. Two other critical influences on RDD-Net are SE-Net and SK-Net, both of which focus on attention mechanisms. SE-Net, which is also known as squeeze and excitation network, introduces the notion of a squeeze and excitation block, something like this, to apply channel-wise attention. The squeeze step uses global average pooling across the spatial dimensions, collapsing each channel into a single scalar that reflects its overall importance. Then in the excitation step, a small fully connected network learns to reweight those scalar values, essentially deciding which channels are most crucial for the task. Some channel gets boosted or excited, and others are suppressed if they carry less information. This mechanism drastically improves representational power with only a slight increase in computation, making SE-Net a top performer in image classification. SK-Net, known as the selective kernel network, builds upon SE-Net's channel attention concept but expanded it across multiple branches, as we can see over here. Imagine having two parallel streams of different kernel sizes, like 3 times 3 and 5 times 5. After each branch processes the input, SKNet uses a learned gating mechanism to selectively fuse these streams, channel by channel. This means that the network can adaptively decide which kernel size is more relevant for a given input, similar to Inception's multiscale approach, but with an attention-based selection. Overall, SKNet introduced a more dynamic approach to handling features from various receptive fields, blending them with a trainable attention mechanism. Together, SENet and SKNet gave the field powerful ways to emphasize important channels and spatial features, providing a direct blueprint for ResNet's own split attention design. With these historical foundations, we're ready to dive into ResNest itself, which introduces the split attention blocks. ResNest inherits cardinal groups from ResNext, but introduces a new hyperparameter called radix. If cardinality is how many parallel branches are in a block, radix determines how many sub-branches are within each branch. For example, here we have two cardinal groups, 1, 2, in the ResNest block. And then for each cardinal group, we have two radixes. So 1, 2, 1, 2. So then we will have 4 sub-branches, 1, 2, 3, 4, in a single ResNest block. Each subgroup works on a distinct portion of the feature channel, which is then merged at the end with an attention mechanism. Each subgroup performs typical 1 times 1 and 3 times 3 convolutions. Then for each cardinal group, we also do a global pooling to capture channel-wise statistics. A small fully connected network then learns how to weight each subgroup's output. This step is similar to SENet's squeeze and excitation, but done per group with the possibility of multiple splits. This dynamic weighting is called split attention. The network decides which sub-branch features to emphasize or dampen, informed by the global context. Now, going more into the implementation of radix major, conceptually you could arrange these channel splits here into cardinality major or radix major. Radix major means we group channels so that all sub-branches belonging to the same radix index are physically adjacent in memory. Same radix index, such as split 1 here, and so on. By doing so, we can implement the sub-branch computations as a single grouped convolution, taking full advantage of hardware parallelism. This leads to a more efficient training and inference pipeline because we don't need extra channel shuffle or reordering steps. Everything is already aligned in a way that standard CNN operators can handle optimally. There are also some other tweaks, like replacing strided convolutions with average pooling to preserve more spatial information, perhaps advanced regularization techniques, or other training strategies to further stabilize learning. Now, what's noteworthy is that ResNest achieves all these benefits, multipath grouping and advanced attention, with only a marginal rise in parameters relative to a plain ResNet. It also scales well to deeper networks and consistently outperforms baseline ResNet on classification and other tasks. Now, let's bring this home by stressing why ResNest is so relevant for our domain generalization context, especially for binary classification like glaucoma detection. ResNest essentially combines the strengths of SENet's channel focus and SKNet's multi-branch approach. The result is a flexible split attention block that highlights crucial features more effectively, even when data comes from varied sources. Like ResNext, ResNest uses cardinality for multiple parallel pathways, but radix adds yet another layer of refinement, sub-branches within each path. This makes it adept at capturing nuanced variations, which are common in medical images taken under diverse conditions. Despite these complexities, the radix major arrangement ensures that ResNest remains relatively lightweight in terms of extra compute and memory overhead. This efficiency is crucial when deploying models in real-world healthcare settings with limited resources. In medical imaging, such as fundus photography, different clinics may use different cameras, and this creates a domain shift, which is the problem for our paper. ResNest's robust attention structure and multi-path approach helps the model generalize better across these shifts, ensuring it doesn't overfit to a single dominant domain. This is essential for diagnosing glaucoma reliably in diverse clinical environments. Finally, having laid out why ResNest is our backbone of choice, we can now move on to the specific novelties introduced in this paper, or 3 key modules, and see how they integrate seamlessly with ResNest for better domain generalization performance. We'll start off with the joint data feature augmentation with domain randomization component. For brevity, I'll start to refer to this as DFA, data feature augmentation. So, in this component, we introduce a method to jointly augment data and features by incorporating a domain randomization strategy. The primary motivation here is to expand the diversity of feature styles the network sees during training, making it more robust to domain shifts. The key idea here is to randomly sample data level and feature level augmentation statistics from a uniform distribution, eventually combining them to form an augmented features. It's actually easier for me to explain this through the formula, and in the following slides we'll also see more formulas explaining other components. I'll try my best to go through these formulas as simply as possible so we can understand things intuitively. So, here we can see the formula. The whole idea here is to output augmented features that is good for domain generalization. R here is an operator that applies augmented feature transformations, basically an augmenter. And the augmenter for data level can be like cropping or flipping, this one here. And in feature level can be in terms of channel statistics like mean or variance, which is this one here. S1 is the output of the first convolutional layer from the backbone that this paper uses, ResNest 50. So it's the shallow feature after the first convolutional layer, this S1. And lambda is a random variable from a uniform distribution that outputs either 0 or 1. 0 to 1. So then X, we can just think of it as the raw input data, basically the fundus image. So we can compute the output feature that takes in the raw input image Xi through a linear combination of the augmented original input and the augmented feature from the first convolutional layer. When lambda is closer to 1, so this part here, the output is dominated by Rxi, meaning we rely more on augmentations applied to the original data. When lambda is closer to 0, which is this part here, the output is mainly by the augmented feature maps after the first convolutional layer, which is the shallow feature here. The lambda taken, this lambda taken from a uniform distribution applies random transformations at both data and feature levels, which covers a broad range of styles such as contrast, brightness, color shifts, so on. And instead of picking only raw data augmentation or only feature level augmentation, this approach smoothly transitions between them based on the random variable lambda. And because the network sees a variety of styles during training, it becomes more domain agnostic, handling unseen data distributions more effectively. So now we can move on to the second component here, which is done right after the combined augmented features from the DFA component. This module merges two complementary strategies for augmenting intermediate features. The first one is explicit augmentation, which perturbs the original style statistics of source domain data by randomly mixing new, random, and original channel-wise means and standard deviations. Second one, which is the implicit augmentation, exchanges the moments, mean and standard deviation, between different feature maps, effectively injecting the distribution of one sample into another. Now again, using a lambda from a uniform distribution of 0 to 1, the closer lambda is to 1, the more explicit augmentation influences the features. The closer lambda is to 0, the more implicit augmentation influences the feature, shown here by this formula. So we can just take a peek at both augmentations separately. First of all, we'll look at explicit augmentation. The goal here is to randomly mix original feature statistics with newly sampled statistics to produce a style-perturbed version of the features. Again, it's easier just to see this from the formula. So, firstly, we have sigma here, which is standard deviation, and mu, which is the mean. For sigma and mu of R, we just take this from a uniform distribution of 0 to 1, in which serves as an artificial standard deviation and mean values, which help broadens the range of possible styles. Secondly, we have lambda, which is taken from a Bernoulli distribution. Just think of this as something that controls how much each channel is stochastically assigned either the original statistics or the new sampled statistics. Now, beta mix and gamma mix here represents the statistics of artificial perturbation, such that it's either heavily dependent on artificial mean and standard deviation, which is this part here with the R, or the original image's mean and standard deviation, which is here with the x1, xi. How much it depends on the lambda value. We then use these perturbations to normalize the features, which is the formula here. Basically, the more lambda is towards 1, the higher artificial perturbations are. And the more lambda is towards 0, the lower artificial perturbations are, such that the normalization depends only on the original feature statistics. The channel-wise appearance of xi is then heavily perturbed with these mixed features, preventing overfitting to the original domain distribution, which again is our goal. It forces the feature to learn domain invariant features due to the mixed feature statistics, which incorporates the artificial mean and standard deviations. Moving on to implicit augmentation, the goal here is to exchange feature statistics across different samples to further diversify the training distribution. So instead of artificial perturbations from the explicit augmentation, we use statistics from other sample images, injecting mean and standard deviation from one sample to another. Here we see implicit xi here being the feature after an implicit augmentation. We scale and shift it by these formulas here. Xi is our original image, while X index represents another sample image's feature map, a glaucoma image from another patient. The scale and shift are derived from the ratio and difference of standard deviations and means as seen here. Scale here is just a ratio of the standard deviation of the other image and the current image, and while shift uses the mean as the ratio, uses the mean. And by using these formulas, we effectively superimpose the distribution of the other sample image's feature map to the current one. This then exposes the network to diverse moment configurations, enhancing robustness by creating a richer set of variations that might appear in different clinical settings. So, through these two augmentation strategies, we can have features that go through either the explicit augmentation, which is the artificial perturbations, or implicit augmentation, which is perturbations through other samples, effectively removing robustness of learned features by reducing overfitting. Through the weight of lambda, we ensure each mini-batch sees a broad continuum of styles and statistical distributions. So, last but not least is the deep-shallow feature fusion. And I think this is the simplest one to understand. In this final component, we fuse both deep stage 4 features and shallow intermediate stages 1 to 3. within the backbone network of ResNest 50 to create a richer feature set. So the ResNest 50 has 4 stages, S1, S2, S3, S4. And typically, deeper features from S4 capture more abstract semantic information, while earlier stages from S1 contain more fine-grained, texture-level features. By leveraging multiple hierarchical layers, the model can capture both low-level details like textures, edges, from the shallow intermediate features, and high-level representations, semantic clues, from the deeper features. Before fusing, we uniformly adjust each stage's output to ensure they are compatible in dimensionality. Convolutional operations, like a 1 times 1 or otherwise, can reduce or expand channel sizes as needed. So here we can just flatten each feature map and finally concatenate them to form a unified representation. Before we do this, we push the features through a CBAM module. So this module is well known in the AI community, and it basically refines the features so that it goes through 2 sequential attention modules. It gives the features a highlight for the most informative feature channels and pinpoints the most salient spatial location within each channel. CBAM can be seen just like a feature refinery of sort, making the features better. So then after refining and concatenating them to the merged feature vector, this one, it is then passed through a fully connected layer or a classification head to output glaucoma or not glaucoma. This deep shallow feature fusion strategy integrates the output of multiple ResNest 50 stages, augmented by the CBAM attention, into a single representation. And by merging information across different feature hierarchies, the model achieves enhanced feature representation. We eventually reach the final complete methodology in this one diagram here. We see the input image go through the DFA module, which then goes through the explicit-implicit module, which is then pushed through the deep shallow feature fusion module. The fused features goes through the linear classifier, which then detects whether the patient has glaucoma or not. Moving on, we'll see the results of this paper to see whether this methodology really works in domain generalization. To test this framework, 2 experiment protocols were designed. Each experiment explores different levels of real-world variability in fundus imaging. The first experiment uses only the Refuge2 dataset, which comprises images captured from 4 distinct fundus imaging devices. This diversity naturally introduces domain discrepancies, reflecting typical clinical scenarios because the images use different fundus imaging devices. They treated the train and validation subsets of Refuge2 as the source domain, merging them into one training pool, and then they leave the test subset of Refuge2 as the designated unseen domain. Because it's partitioned to ensure distinct device or acquisition conditions, this setup simulates encountering novel data distributions at inference time. And the goal here is to assess how well the proposed method performs on unseen device data, using the knowledge taken from multiple known devices. The second experiment uses 4 public datasets: Refuge2, Harvard, Origa, and Ramon. Each dataset originates from a unique institution or device setting, creating 4 distinct domains. Like in the real world, it would be 4 hospitals, for example. This experiment adopts a leave one domain out approach, which merges 3 domains, like, for example, Refuge2, Harvard, or Origa, into the single source pool for the training, and then leaves 1 dataset out for the testing, such as Ramon. So this scheme rotates across all 4 datasets, ensuring each dataset serves as the target domain once. And this mimics real-world scenarios where training data comes from multiple known institutions, but the model must generalize to a new unseen institution or device. So you can also see the training setup that they put here, binary classification, the batch size, optimizer, the learning rate, and the number of epochs. So first we'll see the first experiment, which only uses the refuge2 dataset. We can see here in the table that RDD-Net at the bottom there achieved SOTA, beating all other previous methods in terms of the accuracy and also the area under curve. So we can see here RDD-Net is actually pretty good and improves upon other previous methods in the past. Experiment 2, which I prefer more because it reflects more real-world scenarios, is the one with the 4 public data sets. And we can see here on the first row, it represents the data set that is being tested. So let's say refuge2 here. Refuge2 is unseen, being tested, and all the other ones, Harvard, Origa, and Ramon, is the one being trained. And we can see that RDD-Net beats the other proposed methodologies, the other papers, within the average. So it has a higher average than all other papers, achieving SOTA as well. And this is the ablation studies, which shows how each module improves domain generalization. And I think this is pretty important because we can see here that on baseline, only the ResNest 50, it does 77.87 here on average. But if we used every single module, the DS, DFA, the explicit, implicit, this is deep shallow, we can see that it keeps on improving with using every single module. So we can see that every single module does serve a purpose in domain generalization. So going through the reproducibility demo, we can evaluate whether those results put on the paper are true or not. So this is how I reproduced the experiments. They have a GitLab link on the paper, this one, and I set up the environment with Anaconda with this one. I used just one 28A, it's not that bad. And then the code itself, I tried to run it immediately, but it required just small changes, like putting this BCE with logic loss, or just some path changes here. And then we can just run this whole line here to train for the second experiment, to do the leave one domain experiment. And we're leaving Ramon and only training on refuge2, Harvard, and Origa. So here we can see the results. The baseline results, which is only the ResNest 50 without any modules, achieved 80 on mine, and on the paper it says 82. And the result with all 3 modules, the deep shallow feature fusion, the DFA, and the explicit implicit, reaches 82 on my demo, and on the paper it's 84. So it's a 2% increase from baseline to the 3 modules. And you can actually see from the ablation studies here that it's 82 here and 84 with all the modules. And this is baseline, this is with all the modules. So 2% increase. So the experiments show to be quite true, that the 3 modules does improve performance on domain generalization. However, there is a discrepancy of 2%. So 80 from my demo and 82 from theirs, and 82 with all 3 modules and 84. So there's always a discrepancy of 2% in accuracy. And I hypothesized that this 2% discrepancy is because of the minimal changes that I did during the when trying to run the code, like the BCE with logic loss, or maybe some other slight modification. So all in all, we can still show that the modules does improve on accuracy, on performance. And that is all for the presentation today. Thank you for listening.